Hi everybody, I'm Rashid. So we'll continue to talk about probabilities distributions, and in this video we'll tackle frequency. So here it's a better idea to give, for example, let's say a percentage. If you say 50% did this, then we get a better image than if we say 5 people did this. Then is it 5 out of 10, 5 out of 20? Here we have Miss Jones. One has two options going to dealership A and B, and she was provided with data for the weekly sales for in dealership A and B. And as you see, dealership A, for example, had so if we add these numbers, let's say 2. And I put here the other tables to make it easier for you to see, and also to make it a little bit quicker, because these, once you get to this probability, it consumes time. So if we add these, then we have 52, and if we add these, we get 104. So the frequency of cars in weekly sales in table 1. Then if we use the kind of the ratio or the percentage or the fraction, so 2 out of, right, 2 out of 52, that's this one, 0.04. Then we do the same thing for each one. Then 20 out of 104, we get this. Then we continue and fill up table 2. So the outcome is x1, x2, and so forth. Then the frequency is, how many people drive a foreign car? 5 people, right? That's a frequency. What is the relative frequency is when you divide F1 by N, and here N is 52 and here N is 104, all right? So it's not a difficult subject to know, and we can move on to 7.3. And in the homework you do a few examples like this, and you'll have a better understanding to it. And so what follows these is, of course, the histograms, which the majority will not have an issue in understanding. In each histogram, the probability of an event E is the sum of the areas of rectangle corresponding to these outcomes, all right? So you'll set up histograms, and that's not a big deal for this. So I would say to review histograms and do some exercises. All right. So if I want to show an example here, let's say what that means. You'll see just a plot. So for example, if we have in an experiment some outcomes, they are 0, 1, 2, 3, 4, 5, which is the frequency here. And let's say 0 showed up 3 times, this one 4 times, and this one 23 times, and this one 27 times, 17 and 6, right? And of course, you do relative frequency, which you add these to get the n, which is 90. Then you do 3 divided by 90, right? 3 divided by 90, and you get 0.03. And you do the same for the others, so 0.16, 0.26, 0.3, 0.19, and 0.07. Remember that probability property. When you add these, you should get 1, right? That's when you find or you check whether they're correct or not. So the histogram idea is just this numbers plotted here. If I do the 0, 1, 2, 3, 4, 5, right? Let's say because this is the highest 0.3, so let's say this is 0.1, this is 0.2, this is 0.3, right? So 0.3 happens at 3, right? Something like this. And so for 2 we have 0.26, let's say this, and for 1 it's 0.16, and 0 we have 0.03 small, and for 4 we have 0.19, it's close to 0.2, and for 5 we have 0.07, again small, little higher than the other one, but not. And of course these histograms can be colored. Is the area. So this is relative frequency distribution for the for these outcomes, whatever they are, when there is 5, let's say, experiments for 5 tosses of this coin, or 5 experiments. All right. So as you see, they're not bad. Then you present, you do a few more, but the important parts are going to come up in the next videos. So let's talk about 7.3, which is binomial trials. And in this section, we fix kind of the attention to the simplest experiments, those with just 2 outcomes. And these experiments called binomial because 2 trials, or Bernoulli trials. So if you're interested to Google this, also you can use Bernoulli trials, right? And they occur, of course, in many applications. There are some examples. When you toss a coin, when you administer a drug to a sick individual and classify the reaction, whether it's effective or ineffective, you know, stuff like this. The example we saw with the light bulb in previous video, whether it's defective or not defective. So the outcomes of binomial trial are usually called success and failure. All right. So success and failure. And of course, we need to have no connection and so forth. So let's look. We will always denote the probability of success as P. And since the other one will be 1 minus P, right? So it'll be Q, which is 1 minus P. And consider, of course, a binomial trial and following experiment. Let's say repeat the binomial trial n times, and you observe the number of successes that occur. And, you know, you assume many things. Let's just explain this first. The binomial probability formula is given, you know, this way. And I'll explain it with this. So we write this here with x equal k to denote that the probability of x equal k, namely the probability that k of n trials. So the probability k of n trials result in success. Okay. As we saw in previous experiments, like this example we just did, when you toss the coin, you can find probability distribution of x by using the counting methods and basic principles, right? So to the right side, we know the terms of the binomial as p and qn. So we say that x is the binomial random variable, right? So x and we have the with parameters n and p. All right. This derivation of this equation 1 that we have is, if you're interested, you can Google it, or you can look at it in the textbook. This is one of the famous formulas. So let's denote that x is the number of heads, for example, in the tossing coin experiment of like the one we did is 7.2. Then x is a binomial random variable with parameters half. So if we go back to this example, you know, here that I did of tossing the coin, you know, when you toss the coin, you only have two probabilities. So the probability is half. So example, I'll toss the coin. And we do this 5 times. Then let's look at the calculation of this particular variable. All right, so k will go that 0 and 1 and 2 and 3 and 4 and 5, right? Then now it's gonna go let's say 1 over 32 over 32, 10 over 32, 10 over 32, 5 over 32, and 1 and 32. So if we use this formula here, which is called 1, as you see, n is 5, k just k, because it takes 0 and 1 and this and this. Then we have p to be 1/2. Let's just put it in parentheses with k. And q. So how are we going to find q? Is 1 minus p, which is 1 minus 1/2, which is 1/2. All right, so 1/2 and n which is 5 minus k. So this is the setup. And as you know, these formula, as we did in previously, for the combinations to calculate these, probably you want to use the calculator, and you have the buttons there. If you use that TI-2XA, you have the buttons in it, or any scientific calculator, you'll be able to figure out. Of course, we need to expand the formula, and then we will calculate this. Okay, so how did we get, of course, these values in the table? Let's show, let's say we need some space here, and let's do it next to this one, because I need to show that of course we're going to use this formula. So let's do for this first one, right, which is this, which means k is 0, but n remains to be 5. So so here the formula, this top one, is going to be 5, 0, 1/2, 0, 1/2, 5 minus 0. Okay. And now if you're not using, let's say if you're using the formula right here to show it, I'll show you how. Then for this 5, 0 here to calculate, you're going to do 5 factorial over 0 factorial, 5 minus 0 factorial, which is, if you do 0 factorial, you get 1. And this is 5, and 5 factorial, you get 1. So this is 1. 1 times 1 to the 0, there is going to be 1/2 to 0 is going to be 1. And 1 over 2 to the 5th, because 1 to the 5th is just 1. And so we have 1 over 32. Okay, so that's the first one. Let me show you the second one. So the second one, so you can see how the formula works. You're going to substitute, as you see, as I mentioned, k takes 0. We did the first one. Now let's do the second one. K is 1, but n is 5. So 5, which is this formula, right? I set up in general here. So 1, then 1/2, 1, then 1/2, 5 minus 1 would be 4. All right, so here 5 factorial or 1 factorial, 5 minus 1 factorial. All right, so here you get 5 factorial. 1 factorial is 1. 5 minus 1 would be 4 factorial. So here, if you do this operation, you get 5. 1/2 is just 1/2, and this is going to be 1 over 2 to the 4th, which basically means here 2 times 2 to the 4th, which is 1, is just going to be 5, 2 to the 5th, which is 5 over 32, which is this one. All right, so you set up this, give you some time to figure out, but that's how we set it up with k for that example that we did in 7.2, right? Then I'll do the other example. I think I will have to clean this to do the next example. Okay. So once you write this down, then you move on to the next page to solve this example. And So do the second one, do the third one, do the fourth one. This way you can see how the formula works. And this is not the binomial theorem. This is the binomial probability formula. All right. And that's it. So we move on to the next one. So now let's see an example. So now let's solve this example. You can pause the video and work out and then fast forward it afterwards. So. Okay, I think that's at least that's better. So we have a plumbing supplies manufacturer produces faucet washers, which are packaged in boxes of 300. Quality control studies have shown that 2% of the washers are defective. So you see two outcomes, it's either defective or not defective. What is the probability that a box of washers contain exactly 9 defective washers? All right, so the probability that is given is 0.02, which is then the complement would be 0.02, so 0.98, and the n is given, which is 300. So the probability that 9 out of 300 washers are defective will be, so that's the 300 for the N, the 9 for the K, P is 0.02, and with the K there, and Q, which is 0.98, with N minus K, so 300 minus 9, which is 291. All right, so this one comes from 300 minus 9, which is this thing here. All right. So as I recommended previously, these you will use the calculator to set up instead using the formula each time. And I also showed, if you want to use the formula, how you calculate these. So the sometimes they're, they take time to do by hand. So for these, it's recommended to use technology pretty much. All right, and you should get 0.14 or 14%. So let's look at the problem again and understand it. So quality control studies have shown that 2% of the washers are defective. All right. So what is the probability that the box of washers contain 9 defective washers? That probability is 0.14, which is 14%. So we can do more examples. Let's do one more here. The recovery rate for a certain cattle disease is 25%. So the target you're looking at, this is what makes it easier for these. It's what you're given is the P, right? and the number there is the N. So if the 40 cattle are afflicted with the disease, what is the probability that exactly 10 will recover? All right. So the 10 is the K, and you know now what to do from there. If you set it up, I think by now it looks clear, right? 0.2510, 0.7530,